Okay, now let's look at this practical as well. The third one, use of a sonometer to determine the frequency of a tuning fork. Okay, so just understand the topic of this. Using a sonometer means something like this. Okay, sonometer box is something like this, right? Okay, so it has two bridges here and it has a wire attached like this, right? Okay, and it has a pulley here, so we can keep a mass like this, right? We can use these apparatus to determine the frequency of a tuning fork, right? Now let's see how we can do that. Okay, I'll explain using this diagram. The thing is, uh, now you know vibration in a stretch string, right? Those theory parts you should know a little bit. Now you know that stretch strings have these sorts of overtones like this. They can be like this, can be like this, right? Like this. Okay, there are certain harmonics, overtones, those things you learn, right? So likewise, if we keep a stretch string and if we attach a mass, right? If we attach a mass and if we make this vibrate, it will produce a certain frequency. It will produce a certain sound. Okay? It will produce a certain frequency. Okay, it can produce a certain frequency, right? Um, what we do is, okay, what we do is, now let's say you have a tuning fork like this. It has a frequency of simple F. This thing will also produce a certain frequency. Okay, let's say this simple F is 500, just for example. Okay, let's say this thing produces only 400. Okay, this thing produces only 400, but we can do something. Okay, we can adjust this apparatus. We can move the mass down, we can change the length and make this 400 equal to this 500. Did you understand? We can make this 400 equal to this 500. Okay, we can make this 400 equal to this 500, right? Let's say the mass we use is 1 kilogram for this apparatus and we made them equal. Okay, and we calculated the length. Okay, you have 1 kilogram mass attached, you have a tuning fork of frequency 500, and initially you see that only 400 hertz is produced using this sonometer. But what do? You adjust the length. You adjust the length such that uh, the sonometer box also produces 500. Later we'll see how we can observe that. Just get the idea, theoretical idea. And then you note down the length. Okay, so for 1 kilogram, you have this much length. And then you go for 2 kilograms. You go for 2 kilograms and you keep the tuning fork near. But you find that the frequencies doesn't match. Then you again change the length. Let's say this is L1. And you find at a certain length, the frequencies of both these become equal. Then you note it down as L2, right? So likewise, you take certain plots, take certain values of what? Length versus mass. It should be actually length squared according to the equation. That means the mass we attach to this system is our independent variable. The length we measure is the dependent variable. Those two are totally different things. They are not related to frequency. They are related by equation, but like they seem to be totally different things. But we use that relationship. I mean, the relationship between the mass we attach and the length. That relationship to calculate the frequency of a tuning fork. Okay, that is how we get that. Okay, so you can, if you didn't understand, you can go back in the video, right? Just pause it, go back. Like if you didn't understand one time or two times, just watch it 3 times. Try to get grasp the concept. Okay, practical details we'll discuss. Okay, I mean, like, how can those become equal? How do we know whether they are not equal or equal? How do we change the lengths? Those things we'll discuss, but this is the theoretical idea behind this practical. Now let's look at the equation. So if you take, let's say we normally take it as its fundamental resonance, okay? Like this. There's a pulley attached, there's a certain, so this is our box, okay? This is mg, this is t, right? So we know, let's say this is capital mg, right? We know this equation v is equal to f lambda. Now we are assuming fork frequency equals box frequency. We are assuming this, okay? We are assuming the fork frequency is equal to the box frequency. And we know V is equal to root T over M. Right? Tension divided by mass per unit length. That is the equation for speed of sound in a stretched string. Okay. Frequency will keep like this. This is the frequency of the sonometer box and also the frequency of the tuning fork, because they are equal in the situation which we are considering now. Okay, right. So we know lambda. So this is like, if you take a wavelength is something like this. So this is half of lambda, right? So here we can say this length is lambda by 2. Therefore, lambda is equal to 2L. F into 2L. So F is equal to what? 1 over 2L times root TOM. We get this equation. And now look at this. We are going to modify this a little bit. Okay. I'm going to like, we should take this L as the independent variable, L as the dependent variable, right? Because according to the mass, this is the independent variable. This simple L changes. But like, you might wonder, where is this capital M? It's not included, even included in the equation. It can be included easily because tension is equal to capital Mg. Right? Okay, so let's see. I'm going to build this little by little. I'm going to take this L to the left. Okay, so L is equal to 1 over 2f times root capital Mg over simple M. Okay, so I can square this. L squared is equal to 1 over 4f squared into capital Mg over simple M. So L squared is equal to, right? This capital M should be my x. X means, I mean, the dependent variable. Okay, so G over 4f squared M into capital M. Now we get this, right? So this is sort of y is equal to mx. You see, notice this. Now what can we do? Just, it's the same story, right? You will, like, when you study this, you will get bored of repeating the same story because it's a y equals mx graph. We take a mass 1 kilogram, okay, and by some practical things, practical procedures, we find the position, find the moment when these two frequencies become equal, and then we measure the length. Okay, so for 1 kilogram, we take, let's say we took the length as 2 centimeter, then we are taking the square of it, that is 4 centimeter. So for 1 kilogram, our y value for x equals 1, y will be 4. All right. For x equals 2, y will be another value. Likewise, we are going to plot a graph. Okay. Then we are going to get a gradient. That gradient is equal to what? G over 4f squared m. So we can say f is equal to 4 over, sorry, uh, g over 4m times the gradient root. Can I get the frequency simply, right? So I hope you understood this. Okay. Using this equation g over 4f squared m, we can calculate the gradient and we can get the frequency, exact frequency of the tuning fork. Okay. So everything is okay, but there's one problem. Like, how can we ensure that the frequency produced by the sonometer box, I mean the string on the sonometer box, is equal to that of the tuning fork? How can we ensure that? What I do is, just remember this, we keep a paper rider, a small paper which is bent into a shape like it can stick, something like this. And then, okay, when these two frequencies get equal, there's a special thing happening. Okay, if you vibrate, if two sources have the same frequency, okay, in physics we call resonance is occurring. Okay, we call that uh, observation as resonance. Okay, see, when an object is force oscillated, that means this string is force oscillated. Okay, the applied frequency is equal to natural frequency. Okay, so the applied frequency means the frequency from the tuning fork is equal to this thing. When these two frequencies get equal, what happens? Resonance occurs. When resonance occurs, there is a very high amount of energy being created. Okay, that's like sort of magic, but that's what happens. So due to that, the paper rider will get flown off. Okay, so we keep a paper rider. We initially put 1 kilogram, and we let the string vibrate. Okay, and then we keep the tuning fork closed, but still the paper rider is not going up. That means these two frequencies don't match. Okay. Now what we do is we change the length little by little. We can pull the string, right? We can pull the string, or we can change the distance between the two bridges. That's what we should do. Not pulling the string. We should change the distance between the two bridges, and at one moment it will start to fly off. So now we are sure that the frequency of the sonometer wire is equal to the frequency of the tuning forks. Tuning fork. So now we can apply the equation and surely say that for this mass, let's say 1 kilogram, the length square is this value. We took one reading. Likewise, we should do at least 5. Okay, and then we should repeat the procedure. Right. So that's all about the practical. Okay. So understand this properly. If you didn't understand, that's what I repeated. Like go back and watch it again. What is an accurate way to get the resonance frequency? See, this is what I told. Place a paper in the middle of the wire between the two bridges and increase the gap until the wire is torn out. This is at the fundamental resonance. Then note down the length and mass. Very simple. Where do we keep tuning fork? Why not other places? We keep it on this. Yeah. Now that's an important point. Like if you take the tuning fork, we can keep it in the air very close to the wire. Or else we can keep it on the wire. Or else we can keep it on the box. So normally we keep it on the box. Okay. Like why don't we keep it on the wire? Because if we keep it on the wire, right, pressure will be applied to that point. And that point of contact will be a displacement node. I mean, it can make things complex, right? If you keep the tuning fork on the wire, see, this is the vibration. If you keep it somewhere here, the vibration can be something like this. So we don't do that. We let the wire naturally vibrate. If it is in air is also okay. Like it don't do any disturbance. But the thing is, the vibration won't be strong enough. If we keep the tuning fork in the air close to the sonometer wire, the vibration won't be strong enough to be transferred. So we won't be able to observe the resonance due to that. The best place to keep is the sonometer box. Okay. Why do we start the practical keeping minimum distance between the bridges at first? Now this is very important, right? So when we do this practical we normally do for fundamental resonance, right? I'll explain that as well. Like why is it easy to detect the fundamental resonance? Because at fundamental resonance, remember these points, right? The vibration amplitude is high. Therefore, energy is higher. Okay. So at fundamental resonance only, we can say that like there's a very high tendency for the paper rider to be blown off at fundamental resonance. So due to that reason, like it is easier to detect fundamental resonance. But there's another problem. Like if we want to detect fundamental resonance, how do we know that it is exactly the fundamental resonance? Sometimes it might be the first overtone, right? Who knows? Okay. So due to that reason, when we do the practical, we start from the minimum possible distance between the bridges. We keep a very small distance and start the practical and increase it little by little. Okay, we increase it little by little. Let's say for 1 kilogram, you started at the minimum possible distance. Increase little by little, got resonance. So you can assure that this is fundamental resonance because you started from the lowest point. Okay, and then for 2 kilograms, you should repeat it. Again, you start at the minimum distance, drag it little by little, and now you can ensure it is fundamental resonance. So that is the points which are covered here. What happens to the wave when traveling up along the wave? Why? Hmm. This point I can't even. That might be a different point that I have to. Don't worry about that, right? Let's go to the next one. Which values of L have the highest accuracy? Largest values, right? If the length of L is greater, like uh, there. Suppose that there are two people. One has a 10,000 rupees salary. One has a 10 lakh salary. If the 10,000 rupees salary person lost 5,000 rupees, he has lost half of his value. He will be very worried, right? He'll be like, he will be down. But if the 10 lakh salary person lost 5,000 rupees, he won't even mind that. Okay. So the highest accuracy or the lower percentage error, okay, is felt by the largest values. Percentage error being low means something related to that example I told. The instrument measurements needed to get M given in theory, mass per unit length. This is important. Okay. So in the practical, you should give attention to all uh, finite details, right? So here to do this practical, we should take the wire and calculate the mass per unit length of that wire. So to do that, uh, mass per unit length means we can say mass over volume means density. Mass over unit length means length means volume over cross sectional area. So we can get the diameter of the wire to calculate the cross sectional area, right? Wait a minute. So here we can say, now I can write this like this. Okay, mass means what? Volume into density, right? So mass means area into density divided by length. So mass per unit length means A rho. Okay. So normally you can find the density of a material using the internet, right? If the wire is copper, it has a certain specific density. So the cross-sectional area can be calculated using, the diameter of the wire should be calculated to get this cross-sectional area. So you can use a micrometer screw gauge, right? And this is also important, this point, see. We should start with the higher mass to ensure at maximum length while it is not exceeded. So this also remember, like we normally start with the highest possible mass. Okay, I mean not this simple length like this equation. In this equation, you have this thing, this capital N, right? Okay, so we normally start with the highest possible capital N. Okay, we start with the highest possible capital N. There's a reason for that, right? Now let's say, now listen to this very carefully. We started from, let's say, 1 kilogram. Okay, we got the length, let's say 1 centimeter. And let's say the length of the wire is 3 centimeters. Okay, the length of the wire is 3 centimeters. And we went to 2 kilograms, the length is 2 centimeters. No problem. We went to 3 kilograms, the length is 3 centimeters. No problem. We went to 4 kilograms. Now what happens? The wire length is exceeded. You won't find any resonance because you won't be able to make this length 4 centimeters. Okay, so there's a problem, right? If we start with this lowest mass, assuming that we know everything, we will be stuck in one point. There's a possibility that we will get stuck. Let's say we start from the highest mass. We are saying mass 3 kilogram is equal to 3 centimeters. Now this is almost the length of the wire. So now we know, like, we cannot, now we should group this into 5. So what we do is, we don't take 2 kilograms next. We take something like 2.4 kilograms. It will give 2.4 centimeters. Then we'll get something like 1.8 kilograms. Then we can categorize it or group it accordingly, the ratios, right? Then we can get 5 readings without any problem. Because if you start with the smallest one, you don't know where it ends. But if you start with the largest possible one, you know where it ends, and accordingly you can categorize the readings. So that is also important, right? So remember, just get the point, understand everything, but also memorize how to write that. So we should start from higher mass to ensure at maximum length the total wire length is not exceeded, right? Okay. Different ways of question 2. Okay. Give advantage. See, that's what I told. Now they are telling, why don't we keep it at other places? They can ask it like this: give advantages of keeping tuning fork on the box. Okay, this is also very important. Efficient energy transfer, air column vibrate with maximum amplitude, so we can get the uh, resonant frequency, right? So remember these questions and the answers as well, right?